Okay, so now we want to talk about the last component that affects reaction rate, which is a catalyst. Although you don't see it written explicitly in the Arrhenius equation, the catalyst actually affects both the value of the EA and the orientation factor. I'm just going to generally talk about catalysts and then afterwards give a couple of examples of different types of catalysis that could occur. A catalyst, it's a molecule that provides an alternative reaction pathway for your reaction, and this reaction pathway is going to be lower in activation energy. So it helps you go through to the product with a lower barrier, and that's why the reaction has a higher rate. And this is exactly how catalysts impact the Arrhenius equation. So if you look at the Arrhenius equation, K equals A, e to the negative EA over RT, what the catalyst does is it affects the activation energies. When the catalyst comes in, that value of EA will actually drop. So if the EA goes lower, then the negative EA over RT will also becomes less. And then of course the E to the negative EA over RT, which is the same as just the reciprocal of that expression. If the EA over RT gets smaller, then this whole expression here will go up. If that goes up, that K, rate constant, also goes up, which means the rate also goes up. So you can see that when you add catalyst, the effect is on the activation energy being lower, but then eventually it will lead to an increased rate of reaction. Now, exactly how does it lower the activation energy? Well, it does it by giving the reaction a new path. So here's an example. You have your original uncatalyzed energy diagram, which is shown in red there, and you can see that there is an activation energy associated with that reaction. Now, when you add a catalyst, what the catalyst does is it interacts with the reactant in such a way that now the reactant goes through a different path in order to get to the product. It's still the same reactant, it's still the same product, okay? So that delta H component doesn't change, but how it gets there changes. So in this example, instead of one-step mechanism where reactants go directly to transition state to product, now it goes through one transition state, forms something called an intermediate. I'll talk more about that term later. Goes to another transition state, forms another intermediate, and then eventually goes to the product. That's one example. It doesn't have to always go through this type of route, but as you can see, the overall level of the transition state for either one of these two is lower than the original transition state that was located here. So that makes the activation energy less, which makes the reaction rate goes faster. Now, there are two different types of catalysts that could occur. The first one is what we call homogeneous catalysis. This means the reactants and the catalysts are in the same phase, same state of matter. So usually they're all aqueous. That would be the most common one in homogeneous catalysis. We often see either acid or bases acting as catalysts in this context. So you would say it's an acid catalyzed reaction or a base catalyzed reaction because an acid or a base is added to make that reaction go faster. So here's an example, okay? So this is formic acid. It breaks apart into two products, which is carbon monoxide and water. Okay, if you don't catalyze the reaction, this is what actually has to happen. This right here is the molecule of formic acid once you draw out the Lewis structure. The first step that happens is this electron that's shared between hydrogen and carbon has to leave and move towards the carbon, becoming a lone pair. And then the electrons from the oxygen on this side has to pull that hydrogen towards itself to make a new bond. So the result is this molecule right here that I just highlighted. So now you have your lone pair here, and you have this new bond that's formed between the hydrogen and the oxygen. The second step after this is the lone pair from the oxygen in that double bond has to form a triple bond, another bond, and then the electron pair here then moves to the oxygen to form a lone pair, resulting in the final product, which is H2O and then carbon monoxide. Now, this process is very slow because that first step is very slow. There's no reason for this oxygen to want to pull that hydrogen, and that's the step that initiates the whole process. So if you just leave it to temperature alone, this thing is going to take a long time to happen. However, you can make it go faster using acid, which is a proton, as a helper. And it's shown here in the lecture notes. I still have my formic acid, but now I add an acid to the solution. Remember that the first step is the oxygen has to attract a proton. But now there is a proton proton that's positively charged floating around. So there's a stronger attraction to that positive charge compared to the proton that's already in the formic acid, which is not positively charged. That interaction forming that new bond happens faster now compared to what it was before when the acid is not present. Now, once this species forms, then of course that bond could break, okay, because the oxygen doesn't want to form something with 3 bonds like that. So that can break, forming your water molecule. That's one of the products. And then once this breaks, it forms this species, which is really unstable because the carbon has a negative formal charge. So it wants to quickly break apart, generating the carbon monoxide, regenerating that H+, which is the catalyst. That's an important fact about a catalyst. It doesn't actually get used up. It gets regenerated at the end of the reaction. This new path where you form this molecule and then you generate one product first and then the next product, that's a new path that the reaction goes through. So it can be shown in this energy diagram right here. This is the original energy diagram on the left, and then this is the energy diagram on the right after the acid catalyst is added. And you can see that in the catalyzed reactions, even though there are more transition states, the reaction actually goes faster because all the transition states are lower in energy compared to the original uncatalyzed transition state. So the second type of catalysis is what we call heterogeneous catalysis. The idea here is that the catalyst is in different phase, different state of matter compared to the reactants and product. Most often this happens when the reactants and products are both gases and then the catalyst is a solid. If you imagine you have molecules that are floating around here and they have to react with each other in the gas phase. So this is all randomly moving around, right? And sometimes they'll collide with enough activation energy and in the right orientation to generate a product. But you can see that the probability of that happening is not very high. And this is in 3 dimensions in a container. Now, what happens when you put a catalyst that is a solid? So here's some solid catalyst, and the catalyst is going to stick out like that, and it's going to pull down the molecules that are responsible for the reaction. Let's say the catalyst pull down the reactant molecules. Now what happens is, because they get pulled down, now the molecules are much closer with each other compared to when they were in space like that. So pretty much what happens is you've reduced the search space from a 3-dimensional space into a 2-dimensional space, and there's less space to search. Therefore, it's easier to find the correct partner. And when it's easier to find the correct partner, the products are going to be formed in a much shorter amount of time, which means the rate has increased. And so that's how these heterogeneous catalysts typically work. It just reduces the amount of search space, effectively increasing the concentration of the reactants. The last type of catalyst I'll mention just briefly is enzyme catalyst. This is biological catalyst that typically has undergone thousands and millions of years of evolution to catalyze very specific type of reaction that happens in your cell. So it just catalyzes that one reaction. But because they've been fine-tuned over millions of years, they're very good at what they do. The enzyme catalyst will put the industrial catalyst that we talk about here, like the heterogeneous catalyst or the homogeneous catalyst, to shame because they're just so specific. They make things go really, really fast. But the mechanism of these catalysis using enzymes is quite complex. They usually have a molecule that they're catalyzing, and that's called the substrate of the enzyme. It's usually given the letter S, and then the enzyme itself is given the letter E. And the enzyme and the substrate needs to form what we call the enzyme substrate complex, which is ES. And once the enzyme substrate complex forms, the enzyme can then take the substrate and break or rearrange its bonds. Now, these enzymes are not tiny molecules. So remember earlier we talked about that formic acid catalysis, and basically the only thing that helps there is a proton. A proton is the smallest ion out there. With the enzyme, it's very different. Look at this picture right here. This whole gray molecule is the enzyme. This little red molecule is the substrate. So you can see how much bigger the enzyme is compared to the substrate. Once it pulls the substrate in, can do whatever it wants with the substrate because it's so much bigger compared to the substrate. So the substrate, once it's trapped inside that enzyme, that's called the active site of the enzyme. It's pretty much helpless. Enzyme can do whatever it wants with it, break some bonds, generate the products, and then afterwards release it out again as product molecules. And this is why enzymes are so good at catalyzing reaction, because it has that special way of binding to the product, keeping it in there, and rearranging the bonds that it needs to rearrange to make the product form in a much faster time.